Now, we can use transistors as the basic building block for a computer. And to do that, we could connect two transistors back to back. And I know this is probably getting a little bit more detail than everybody can comprehend with such a short introduction. But basically what we have is one transistor that conducts with a positive input, causing the output to go negative. And this negative is applied to this transistor to turn it off. So if this one has a negative on the base, it does not conduct, and it allows this resistor to provide the full supply voltage here since there's no current through it. So with a 1 here, you get a 0 here, a 0 here, and a 1 here. And that allows you to have a counting device so that as you apply an input here to this one base, it'll change the state of this transistor and automatically change the state of this, and they're always in opposite state. So by changing state, you can make this one a 0 and this one a 1, or this one a 1 and this is a 0, and each time you pulse it, it counts to the next level. Now, we were blessed with 10 fingers, so we count with a base 10, but since a computer only knows on and off, it counts with base 1, and it uses 0 and 1 as the values, which are two different values. If we attach another one of these switches to this one from the output here to the input of another one, each time we count from 0 to 1, this one will not produce an output. If we count from 1 back to 0, this one will produce an output, which is a carry, which changes the state of the second switch from a 0 to a 2. So if we cascade or put in a sequence or a row 4 of these 2-bit switches, we now have a 1-bit, a 2-bit, a 4-bit, and an 8-bit, and we can 8-bit, and we can count from 0 to 7, 0 to 8, 9, 10, all the way up to 15. Here's a view of what an integrated circuit looks like inside from a microscope. This is a 3-dimensional view of an integrated circuit. They were invented simultaneously by 2 different companies, Jack Kilby of Texas Instruments and Robert Noyon of Fairchild. And Jack Kilby is also the co-inventor of the handheld calculator and the thermal printer. Here are 3 memory chips that were used back in the 80s. These are 16K bytes, and you can actually see the integrated circuit through a little quartz window and the little wires that are connecting the chip to all your terminals on the outside. And this chip was used for program memory in the earlier computers, which required something called a programmer that would actually write the per-minute program into the chip, and then you would use it in a computer. And if you wanted to change the program, you'd have to completely erase it and then rewrite it. And to erase it, you expose this chip to an ultraviolet light source for about 10 minutes. And after that 10-minute period, all the bits are turned back to 0 so you can reprogram it again. That's the reason we have a quartz lid that allows the ultraviolet light to go through. So much easier now to change the programs and just rewrite them rather than having to erase and put in a programmer, then put it back in the computer. So as I was saying before, we can take 4 of these flip-flops, put them in cascade, and you can see here the counting sequence of 0 and 1, 0, 2, 0, 4, and 0, 8. And that gives you up to 15, actually 16 different values from 0 to 15. And that's where we came up with the hex counting system, where numbers are 0 through 9. But then to continue for the other 6 values, we use the alphabetic letters A through F. If you were working on computers in the old ages, you might only have 8 values to your count using 3 of these flip-flops, and those were octal numbers, 0 through 7. So when you work on computers, you'll find many different circuits that are used to perform the different functions, such as comparators that can compare bits and cause other functions to occur. You can reset counters before they reach their total count to make different bases for the counters. And other comparators can decode the 4 bits and convert them to displays. Here's the display we used to use in the 60s. It's called a Nixie tube, and it's an acronym for numerical indicator experiment. And it consists of a bulb with a screen connected to a positive potential. And then it has 10 different pieces of wire shaped as the letters 0 through 9. And as long as you have no connection to one of these wires that has the number represented, nothing will light up. But if you connect that wire to a negative terminal and allow the screen to be positive, you'll see a glow for that number. And these were used for many, many years, long before we had the 7-segment displays with either LCD or liquid crystal. This is an application of that Nixie tube, 8 of them in a row, to count pulses over a period of time. And these are used for measuring frequency and time duration. They're still used today. This one is over 60 years old and it still functions like new. Today you can go to Amazon or eBay and you can get a retro clock made with these Nixie tubes, although they're a lot more expensive than the ones that you buy that have LCDs or liquid crystal. They look kind of cool, but they are expensive. Back in the early 70s, I decided to experiment and learn a little bit about digital circuits, and I decided I'd make a clock. And this one generates the results with the day of the month, the hour in 24-hour time, the minute, the seconds, and tenths of seconds. And it was just an experiment to learn how to use the digital chips and connect them together and use the Nixie tubes. And it still works, but I don't have it connected up today. If we look at a top view, you can see in this row, we have the 4-bit binary counters consisting of the 4-bit flip-flops counting 0 through 9. And then here we have a row of decoders that convert that 4-bit binary number to a decimal 0 through 9 to light up the tubes. And in this back row, we have some reset chips because for tenths of seconds and the digits portion of the seconds, we go 0 through 9. But on the tens digit of the seconds, we only go from 0 through 5. And when we get to 59, we have to reset because a minute only has 60 seconds and an hour only has 60 minutes. So we do the same thing here. And this chip here resets this chip to 0 when we get to 23, and it gets another pulse indicating it's 23, 59, 9. Then it sets this back to 0 at the end of the day and transfers a pulse to the month digits. And I never added any reset circuits for the month. I just reset them manually at the end of each month. And there's a bottom view that shows what the wiring looks like. So we have wires here from the decoders, from the counters to the decoders, and we have the reset logic here, and we have power wires connecting everything together. And you'll find with the clock kit you're going to be building in this soldering class, everything is so much easier today because we add the computer to the mix. Today we use digital displays such as 7-segment LCD and LED. And here's an example of a 7-segment LED, a light emitting diode that has 8 segments, 7 of which make up the number and a decimal point. So if you want to write a 1 to it, you light up the B and the C segments. If you want to write an 8, you light up all the segments. It just simply takes a positive voltage on the anode and a resistor to limit current and a switch to light up each of the different segments in the display. And this is done by computer. This display here on the right bottom is almost identical to the one you'll be putting in the clock kit. The only difference is the decimal points are displayed as a colon for a clock instead of a counting number with decimal points on the bottom. And in this one, we actually combine all 4 digits by connecting all of the A segments together, all of the B segments together, and so on. So we only need 7 wires for the segments and 1 for the decimal point to control all 4 digits, but we have 4 separate wires to control when each digit lights up. So in this case, we are not able to display all 4 digits at one time. We have to multiplex or timeshare them. And the way that's done is the computer will place the proper bit value on the segment leads in order to display the right segment combination for the first digit in your 4-digit display, which would be the first hour's digit. Then it will actually put a positive voltage on the common anode and light those for a fraction of a second. Then it will change what it puts on the segment display wires to the next digit, and then light that segment and move across and display all 4 of them in sequence at about 30 or 40 times a second. So if you're doing it 30 times a second and you have 4 segments, it's actually writing 120 different values to these segments to display each time display 30 times a second. But your eye has a persistence of vision and you do not detect the flicker as long as it's greater than 24 changes per second. So it looks to you like the LEDs are on all the time. But if you were to take the clock kit and shake it left and right sideways, then you would be looking at each of the segments as they were changing, and you can actually see the different segments lighting up at different times while you're moving it side to side, because your persistence of vision is interrupted because the target that you're looking at is moving. We also have today something called an OLED display, which is an organic LED, and they can be made very thin. They can even be made on paper, and you can roll them up and put them in a device very small and unroll them when you want to look at them. Even a flat screen TV of 65 inches can be rolled up now. And they also have roll-up TVs that have it roll from top to bottom and store it in the top of a table and actually roll up when you want to watch it and then roll down when you're finished watching it. The clock kit they're going to build uses something called a medium density integration chip, which is in effect a computer. It's a microcontroller chip, and the microcontroller is almost identical in function to the larger computers. It's just scaled down as far as the number of bits in the bus and the speed and so on, but it is truly a standard computer design. This is what the circuit of the clock kit looks like. I don't know if you've looked online at the clock kit on the Google Drive share, but in the soldering class, we have all this data logged for you to look at ahead of time. The clock kit has the microcontroller chip here in yellow. It has wiring and buses. It has several other external components such as the display, a capacitor, a resistor bank, some switches to set the clock, a clock crystal, and an output device called a speaker or a buzzer that allows you to use it as an alarm clock with a transistor controlling it, just like I showed you before, where you can use a transistor as an alarm to provide current for an output device. So first we're going to look at the basic internals of the microcontroller to see how a computer functions. There's a block diagram of the exact microcontroller that's used in the clock. It looks very complex at first glance, but if you break it down into little pieces, it's very easy to understand. First of all, we have something called an oscillator, and that generates a sine wave or a square wave of alternating current, and that's used to synchronize all the functions in the clock, and it actually vibrates at 12 million cycles per second. We have a reset signal that comes in that you'll have to create with the external circuitry, and that starts the processor in an organized fashion after power is applied. The reset logic actually sets a program counter to 0, and that is addressing what we call a flash memory. This is where all the instructions or program steps reside, and these are binary numbers that identify each instruction and the operand and tell the computer how to perform that function. So this counter over here, the PC incrementer, is set to 0 when you reset, and then the 0 address is put in the program address register, telling the flash memory to put on the bus the memory that comes from location 0. So your first instruction goes onto this bus, which is called the central system bus. All the devices in this computer can communicate with the central system bus. They can write data to it and they can read data from it. So the first instruction comes down here into the instruction register, and this timing and control logic decodes the instruction register to determine what function is to be performed, and it puts out control signals to all the other different components in the microcontroller to cause that function to be executed. For example, it can use an instruction to read an input port, and let's say your switches are connected to this input port here. It can read them into the port 1 latch and transfer the data to the bus, and from the bus it goes into the processor ALU, which is the arithmetic logic unit. The instruction can then examine that bit content to determine what the switch function is that you're trying to perform. And if it's doing a compare operation to see if a bit is a 1 or a 0, it will put the result or condition code in something called the program status word. That data can come back around the bus and go back in and be available for the next instruction that makes a decision of what to do with that data. If you have temporary data from a calculation, it comes out of the arithmetic logic unit and goes up to the RAM address that's specified when you write to the RAM. So the actual address would go to this register here, and then it would address the RAM, and from that random access memory, that data would be read and put back onto the system bus and used by whatever component needed it. Every time a new instruction is executed, this PC incrementer, the program counter incrementer, will address to the next instruction and put that address in the program address register, so that when the control logic determines it's time to execute another instruction, it will bring that new instruction down, and the cycle repeats over and over again. That's basically how any von Neumann computer works. This von Neumann architecture was actually used in the first computers called ENIAC back in the late 40s. And by saying von Neumann, what we mean by that is it's a stored program computer where the instructions are actually in memory along with the data, so they can be modified and read out, as opposed to a hardwired computer where a control panel is used to control the instructions. So with the clock kit, you're going to be able to read the switches, compute the time, and display the current time. The microcomputer needs short bursts of large current to operate all those switches in it. So we need to filter the power, and we'll see how to do that. It requires a reset signal at startup. An amplifier transistor runs the alarm buzzer with a larger current from the transistor. And we use pull-up resistors for the LED segments. And as I said before, time division multiplexing allows you to display multiple digits by sharing the segment wires. So the push buttons are simply connected to an I/O port. Ground is the 0 or the negative battery return. And inside the computer program, you would actually define what's called a pull-up resistor. It's a logical resistor that you can define inside the computer processor that actually causes this pin to be raised to a positive voltage, which is a 1 in boolean or digital logic. When you press the switch, it connects that pin down to the ground. And even though the resistor is connected to the positive voltage, the resistor now has the entire supply voltage current across it, and the pin goes to 0 volts, and that's a 0 or a logical off signal, whereas when the button is not pushed, it's a 1 or an on signal. So just by connecting a button to the power supply return lead, we can cause the computer to perform different functions. And one button can perform more than one function because you can do a short press and the computer can time how long it's pressed. And if it's less than a second, it can perform one function. But if you hold it down for a second or two, the computer can determine it's a different function and can act differently on that push. As we said before in yesterday's session, a capacitor opposes a change in voltage, and it does that by storing a charge between the positive terminal and the negative terminal. And by placing a capacitor right next to the microcontroller chip, that provides a reservoir of energy such that we don't have to worry about pulling current from the battery over a long wire or a USB cable from your computer that's powering the clock. We have a local reservoir that can provide an instantaneous burst of energy without a loss in charge or voltage. So the capacitor here is used as an energy charge or a filter. And we talked about time constant yesterday and how long it takes to charge a capacitor through a resistor. And here we have a case where we're applying that theory to the reset. And in order to reset this processor, when you first turn it on, we apply 5 volts to the reset line. And as soon as the reset line drops down to less than a volt, that tells the processor to start its operation. That performs a reset. So when we first turn it on, this capacitor has no charge in it, so it acts like a dead short or a wire through and requires a current in order to get a charge on it. We place the 5 volts on one plate of the capacitor, and we connect the other plate to our negative 5 volts through a 10,000 ohm resistor. And now we see the full 5 volts across this resistor while the capacitor starts to charge. And in one time constant, the capacitor charges to 63% of the 5 volt supply. And as a result, it's 63% less than the 5 volts on the right side of the capacitor. And after 3 or 4 time constants, we're actually at 0 volts and no voltage across this resistor. All of the charge is in the capacitor, and that continues to keep the computer in operating condition, and it won't go back to reset unless this goes back up to the 5 volt supply to stop the computer, and then going back to 0, it would reset. But that won't happen as long as we have our 5 volts. So if your 5 volts goes away, this resistor discharges the capacitor in the same amount of time, about 1/10 of a second. And then when you turn it on again, it resets again. So we don't need to push a button to reset the computer. We've used our time constant theory with just a capacitor and a resistor to perform that function automatically every time we turn on the clock. As we said before, a transistor allows you to take a very small current through the base and emitter junction and cause a large change in resistance between the emitter and the collector. So if you do not have a current at the base, the buzzer does not get any power. And as soon as you put a small current between the emitter and the base, this resistance between your emitter and your collector provides a very short resistance and allows almost all of your 5 volts to be applied to your alarm buzzer, waking you up with your alarm clock. Here's a small section of the circuit showing just the microcontroller and what we call a bus that connects the microcontroller output port to all of the segments of the LED display. And as you can see, here we have an A connected to A here. We have a B connected to B here. And so when we look at these identifying labels, these are the logical pin numbers of the chip that tell which output bits the program's referring to. This is the physical pin number of the chip, counting around the chip clockwise, leg to leg. And these are the logical signal name, segment A, segment F, and segment B, related directly to the segments here on this chip. And by the same token, these numbers here are the pin numbers for your LED display chip. So when you're actually making a circuit board, you would connect this 19 pin of your microcontroller, which is function A, to pin 1 of your display chip, and so on down the line. And so a bus on a circuit diagram is normally indicated by taking a collection of signal wires that perform a similar function to each other and wrapping them into a wider lead or wire that shows a direction onto the destination of the signals and where they end up. So rather than having to look at 8 or 9 different wires and follow them, you just follow the names of the signal from one end to the other, and you can understand what the circuit is doing logically. And in order for these LEDs to light properly and display 4 different digits, the computer will first put a value on each of these pins that matches the bit configuration of the number of segments that need to be lit to make that number. And then immediately afterward, it will put the opposite signal on the proper segment lead. And in this case, the segment leads are negative, and I'm sorry, excuse me, the digit leads are negative, the segment leads are positive, and in order to make that happen, this resistor is connected to your 5-volt supply, and this actually has 8 resistors in it. One end of each resistor is connected to pin 1 to the 5-volt supply, and the other end of all 8 resistors is connected to each of the segment leads. So if you just connect one of the digits leads to your negative supply and allow this resistor pack to provide positive to all your segments, it will light up all 7 segments and the decimal point segment. So it's the purpose of these lines here to actually write a 0-bit or pull down to a 0 logic level the segments that you do not want to light, and allow this resistor pack to light the segments that you need to illuminate when the digit signal is set to a negative signal by another port in the processor. So the processor, in writing all this data, has to go through a fast loop over and over again, each step of the loop calculating what the bit configuration is for the digit, and then writing it to the digit, writing it to the segment leads, and then illuminating that digit for a fraction of a second, then moving on to the next one over and over again to display all 4 digits. This is a diagram of what the electronic internal configuration would be of this LED display, showing that your digit lead is common and all your segment leads are separate for each digit, but you would have 4 of these all in a row with all of these segment leads tied together, and you'd end up with 4 separate digit leads going back to the computer so you can control each segment of the display in parallel. A quartz crystal is like an electronic tuning fork. A piece of quartz can be shaved and filed or milled down to a certain thickness, and if you put electrodes with metal plates on each side of the quartz, now when you put electrical current into it and then take the current away, it will vibrate at a resonant frequency based on its physical size and shape. And the one we use in this clock is a little tiny piece of quartz with metal plates that actually vibrates at 12 million cycles per second. And we use 2 capacitors that alternately charge and discharge, and that allows the clock to see 2 different positive and negative going pulses in relation to the ground or minus supply voltage. And these are labeled 30P. And when you look at a capacitor and determine its value, as we said yesterday, the farad is the base unit for capacitance. Microfarad is the standard value for most capacitors used in electronics, but for something that's this slow, this fast switching, you need a very, very small capacitor. And this is a 30 picofarad, which is in effect 30 microfarads, or 30 millionths of a microfarad. Logic gates are used in the computers, and when we look at how logic gates work, we use something called boolean algebra with logic 0s and 1 as their value. A logic 1 is a true state, a logic 0 is a false state. And if you look at the voltages presented in the circuitry, a logic 1 is a high and a logic 0 is a low. And with 5-volt logic, anything over 4 volts would be considered a high. Anything less than 1 volt would be a low. And those are the voltages that the computers use to store their 0s and 1s. And these are some of the symbols used for the logic gates, made up of either resistors and capacitors or diodes or transistors. There are many, many different ways to make logic gates. And all you really need to work with a gate is your 1s and 0s on the input and either a 1 and 0 on the output. You don't need to worry about the transistors or diodes or other functions within the chips that make up the gates. You just connect the gates to perform the logic function that you want to perform. So for an AND gate, the logic states that if either logic says that you need A and B both as a true or a 1 in order to have a true output. A NAND gate is an AND gate with a negate on the output. So basically what we're doing here is we're saying if both A and B are true, the gate says the result is true, but it turns it over and inverts it so the output is false. And that's where the NAND or negative AND gate term comes from. An OR gate uses 2 inputs or more, and if either A or B are true, or both are true, we get a true output. If neither input is true, we get a negative output. And the NOR gate does the exact same thing, but negating the output. If either A or B are true, the gate function is satisfied, but then inverted. So if either A or B are true, the output is false. Another third gate we have is called the exclusive OR gate. And in this case, only A or B can be true for a true output. If both A and B are true, or if both A and B are false, it's always a 0 or false output. But if either one or the other is true, then we have a true output, as compared with the OR, where either one true makes it a 1 output, or both true makes it a 1 output. And the exclusive NOR does the exact same thing as exclusive OR gate, but negates the output. So if either A or B, but not both are true, the output is false. A buffer is just an amplifier where whatever you put in is the output you get. If you put a 1 in, you get a 1 out. If you put a 0 in, you get a 0 out. And it can be used either to allow you to drive multiple gates where the source is not strong enough to drive as many gates as you need in your logic. You'll put a buffer in to add strength to the signal to drive more gates. Or it can also be used as a delay device, because going through each of these gates causes a slight delay, and the electronic designers that define the logic need to keep track of how many gates are in a sequence to determine how long it will take before an input produces a valid output. And buffers can be used to delay the output of another signal so it arrives at the same time as another comparison, so everything works in synchronism. The NOT is simply the inverter, just like on the output of any of the NOR or NAND or XNOR gates, which inverts a logic value, so a 0 in produces a 1 out, and a 1 in produces a 0 out. So now that you've seen all of the different gates that were needed to build computers, you can see the truth table for an actual chip that has gates built in. And in this chip, we have 4 AND gates. You can see that it takes the power source from pin 14, the negative source from 7, and 2 inputs on 1 and 2 provide an output on 3, and so on for the other 3 gates. And your truth table, as I explained on the previous slide, how all the different functions work. So if you get into working with computer logic and do gate analysis, these charts will be beneficial to have at your fingertips until you memorize the symbol and what the gate does. Then you won't need to look at any of these charts again. You'll be able to look at a gate chart and understand exactly what a logic diagram is doing in a complex assembly. One interesting thing is that either NAND gates or NOR gates can be arranged in a combination to make any of the other gates that I've just described. So in effect, all of the gates needed to build a complete computer can be composed of either just NAND gates or NOR gates. And the Apollo guidance computer was actually built with just the NOR gate. And the reason it was done that way is the integrated circuits were so new at that time that it was a real project to get a reliable validation of the manufacture of the chips. And as a result, MIT, that developed the Apollo guidance computer chose to use only one type of chip, and they consumed during the Apollo program 64% of the integrated chip manufacturing of the entire United States. And they chose to use a single NOR gate. And with 28 of those 3-input NOR gate chips, each containing 3 gates, they were able to build the entire Apollo guidance computer. And it was used to guide the Apollo program into orbit around the Earth and release from that orbit and get to the moon in lunar orbit, and then descend to the moon and land safely, then leave the moon, go back up to the command module and dock and rendezvous with the command module, get out of lunar orbit, get back to Earth, get into Earth orbit, and then descend back to the Earth and land in the water, all using these NOR gates in one Apollo guidance computer. This YouTube video that I reference here is a very interesting video that gives you the history of how the Apollo guidance computer worked, but more importantly, it tells about design constraints and how they were able to use the scientific approach to make a very, very robust and reliable computer, and how some of those same approaches to designing a computer can be valuable in making a reliable robot computer. And at the end, some of the interviews with the people involved are very impressive, especially the one about Margaret Hamilton, who was laughed at when she told people that computer design and program design should be done in a scientific controlled manner. But at the end, when they found that in every mission with the Apollo guidance computer, they never had a failure, they actually started to appreciate and recognize the value that her approach toward reliability and control brought to the program. And she ended up with the highest honor available to any civilian in the United States. The Presidential Medal was awarded to her in 2016. So you might find this video to be very, very enlightening and interesting if you have an hour or so to look at it. These are just the other gates that we talked about, and these slides are for reference in the future if you choose to save them. We're almost to the end now. The digital voltmeter. We talked earlier about how the different functions in the digital voltmeter were identical to what's happening in an analog meter, such as the series resistors used to measure large voltages and the shunt resistors to measure large currents. The battery provides the voltage to measure resistance, but we have no meter here. So how do we actually get the numbers to appear on the display telling us the current or the voltage or the resistance? We use several of the building blocks we learned yesterday about electronics, such as time constant with capacitors and so on. And we look at the diagram of a DVM, we can actually see how all this happens. We're going to go ahead to another slide here. This slide here shows comparing your input voltage after going through your resistor network for voltage and current. We compare that voltage in this comparator to the output of a digital analog converter, and a simple mode of making a digital voltmeter, the earlier ones before we use the digital to analog converter, we just use what's called a ramp signal by taking a capacitor charged by a resistor over a short period of time, and we took the output of that capacitor, which starts from 0 and rises to maybe 5 volts. We bring that into the comparator and compare it to our unknown voltage, and when the two become equal, now we know we have a sample of the voltage that we want to measure. So the clock and the control logic stops the counter that's running while you charge that capacitor, and the value in that counter ends up being directly related to your analog input voltage that you measured. So you take the output of that counter, which is just a binary number, run it through a computer, do some algebra, and calculate the actual voltage based on the switch position that you set for your shunt or series resistors, depending on whether you're measuring current or voltage. So moving that rotary switch on your meter actually changes an input to the computer in your digital voltmeter, and that moves your decimal point, and it changes the logic that takes this binary value from the comparator and displays the actual voltage by reading this analog voltage and comparing it to that rising voltage on the capacitor. You end up with a number that's equal to the voltage that you measured. Well, that's all I have for you on computers and meters and electronics today. It's been a pleasure presenting this, and I really appreciate your interest. Thank you very much for attending.